Imagine a place in the universe where gravity reigns supreme, a region so powerful and mysterious that it defies our understanding of physics. This is the realm of black holes, regions so dense that nothing, not even light, can escape their grasp. These cosmic enigmas have fascinated scientists and the public alike for decades, challenging our perceptions of space and time. Black holes are formed when massive stars, many times heavier than our sun, exhaust their nuclear fuel and collapse under their own gravity. This collapse results in a singularity, a point of infinite density, shrouded by an event horizon, the point of no return. The process begins with a supernova explosion, a spectacular event where a star's outer layers are ejected into space, leaving behind a core that continues to collapse. As the core contracts, its gravity intensifies, eventually forming a black hole. The singularity at the heart of a black hole is a point where the laws of physics as we know them cease to apply. It is surrounded by the event horizon, a boundary beyond which nothing can escape. This region is where gravity is so intense that it warps space and time beyond recognition. Beyond the event horizon, the gravitational pull is so strong that it distorts the fabric of space-time itself. This warping effect is so extreme that it can slow down time and stretch objects into long, thin shapes in a process known as spaghettification. Black holes are enigmatic objects, pushing the boundaries of our understanding of the universe. They challenge our concepts of reality and force us to rethink the fundamental nature of space, time, and gravity. Their existence, once a matter of speculation, is now supported by a wealth of observational evidence. Astronomers have detected black holes through their gravitational influence on nearby stars and gas clouds. They have observed the X-ray emissions from superheated matter, spiraling into black holes, providing further proof of their existence. The study of black holes is crucial to unraveling the mysteries of gravity, the evolution of stars, and the fundamental nature of our universe. By observing the behavior of matter and light around black holes, scientists can gain insights into the most extreme conditions in the cosmos. The X-ray emissions from black holes are particularly telling. As matter spirals into a black hole, it heats up to millions of degrees, emitting X-rays that can be detected by space telescopes. These observations have provided some of the most compelling evidence for the existence of black holes. The study of black holes is not just about understanding these mysterious objects themselves, but also about gaining a deeper understanding of the universe as a whole. By studying black holes, we can learn about the life cycles of stars, the nature of gravity, and the fundamental laws that govern our cosmos. For centuries, black holes were thought to be inescapable cosmic traps, their immense gravity preventing anything from escaping their clutches. These mysterious objects, formed from the remnants of massive stars, have fascinated scientists and the public alike. Their gravitational pull is so strong that not even light can escape, making them invisible to the naked eye. The concept of a black hole was first predicted by Einstein's theory of general relativity, which describes how massive objects warp the fabric of space-time. However, in 1974, a young physicist named Stephen Hawking revolutionized our understanding of these enigmatic objects. Hawking, who was already making waves in the field of theoretical physics, proposed a groundbreaking idea that challenged the conventional wisdom of the time. His work suggested that black holes were not the eternal prisons they were once thought to be. Hawking proposed a radical idea: black holes are not entirely black but emit a faint radiation due to quantum effects near their event horizons. This was a revolutionary concept because it implied that black holes could lose energy and mass over time. The radiation, now famously known as Hawking radiation, arises from the complex interplay between quantum mechanics and general relativity. This radiation, now known as Hawking radiation, arises from the interplay between quantum mechanics, the theory governing the microscopic world, and general relativity, Einstein's theory of gravity. Quantum mechanics describes the behavior of particles at the smallest scales, while general relativity explains how gravity works on a cosmic scale. The combination of these two theories in the context of black holes was a significant step forward in our understanding of the universe. According to quantum mechanics, empty space is not truly empty but teeming with virtual particle-antiparticle pairs that constantly pop in and out of existence. These virtual particles are a fundamental aspect of the quantum world, appearing and disappearing in a fleeting moment. They are usually short-lived and annihilate each other almost immediately. Hawking realized that near the event horizon of a black hole, these virtual particles could be separated by the intense gravitational pull. The event horizon is the boundary beyond which nothing can escape the black hole's gravity. At this boundary, the gravitational forces are so extreme that they can tear apart these virtual particle pairs. One particle might fall into the black hole while the other escapes into space, carrying away a tiny amount of energy from the black hole. This escaping particle is what we observe as Hawking radiation. Over time, this process results in the black hole losing a minuscule amount of its mass and energy with each escaping particle. This process, repeated countless times, would cause the black hole to slowly lose mass and energy over time, effectively causing it to evaporate. The idea that black holes could eventually disappear was a profound shift in our understanding of these cosmic giants. It opened up new avenues of research and has had lasting implications for the fields of astrophysics and quantum mechanics. Today, Hawking's work continues to inspire scientists as they explore the mysteries of the universe. To grasp the essence of Hawking radiation, we must delve into the strange world of quantum mechanics. At the quantum level, energy fields rather than particles take center stage. These fields can fluctuate, borrowing energy from the vacuum of space for brief periods, creating virtual particle-antiparticle pairs. Imagine the fabric of space-time near a black hole's event horizon as a turbulent sea of quantum fluctuations. Particle-antiparticle pairs constantly emerge and annihilate each other, their existence fleeting and ephemeral. However, near the event horizon, the intense gravity of the black hole can disrupt this delicate dance. If a pair of virtual particles forms close enough to the event horizon, one particle might be trapped by the black hole's gravity, while the other escapes into space. The trapped particle carries negative energy, effectively reducing the black hole's mass. The escaping particle becomes a real particle, carrying away positive energy in the form of Hawking radiation. Section 4. A universe of evaporation, the slow demise of black holes. Black holes, those enigmatic and powerful entities, are not eternal. They have a life cycle, and their end is as fascinating as their beginning. Hawking radiation, though incredibly faint, has profound implications for the fate of black holes. This radiation, named after the renowned physicist Stephen Hawking, is a theoretical prediction that black holes emit radiation due to quantum effects near the event horizon. This radiation is not just a minor detail, it is the key to understanding the ultimate fate of black holes. As black holes emit Hawking radiation, they gradually lose mass and energy, causing them to shrink over time. This process is incredibly slow, but it is relentless. Over eons, a black hole will continue to lose mass, becoming smaller and smaller. The larger the black hole, the slower this process, but it is inevitable for all black holes. This process is exceedingly slow, especially for stellar mass black holes, which have lifespans far exceeding the current age of the universe. To put it into perspective, a stellar mass black hole could take more than 10 to the power of 67 years to evaporate completely. This is a timescale that is almost impossible to comprehend, far longer than the current age of the universe, which is around 13.8 billion years. The rate of evaporation depends on the black hole's mass. Larger black holes have a stronger gravitational pull, which means they emit less Hawking radiation compared to smaller black holes. This means that smaller black holes will evaporate much faster than their larger counterparts. Smaller black holes with weaker gravitational pull emit Hawking radiation at a faster rate than their larger counterparts. This accelerated emission causes them to lose mass more quickly, leading to a faster evaporation process. In contrast, larger black holes with their immense gravitational pull emit radiation more slowly and thus take much longer to evaporate. In fact, microscopic black holes, if they exist, could evaporate in a fraction of a second, releasing a burst of energy. These tiny black holes, possibly formed during the early universe or in high-energy collisions, would have such a rapid evaporation process that they would disappear almost as soon as they are formed, releasing a tremendous amount of energy in the process. For stellar mass black holes, the evaporation process would take an unimaginable amount of time, on the order of 10 to the power of 67 years or more. This is a timescale that dwarfs the current age of the universe, making the eventual evaporation of these black holes a distant future event that we can barely fathom. As a black hole shrinks, its temperature rises, causing it to emit radiation at an accelerating rate. This increase in temperature and radiation emission continues as the black hole loses more mass, leading to a feedback loop where the black hole evaporates faster and faster as it gets smaller. In the final stages of its life, a black hole would radiate away its remaining mass in a spectacular burst of energy, equivalent to the explosion of billions of nuclear bombs. This final burst of energy marks the end of the black hole's existence, leaving behind nothing but radiation and particles, a dramatic conclusion to the life of one of the universe's most mysterious objects. Section 5. Echoes from the Abyss. The quest for Hawking radiation's signature. Despite its theoretical robustness, Hawking radiation has never been directly observed. Its faintness and low energy make it incredibly challenging to detect, especially against the cosmic microwave background radiation, the faint afterglow of the Big Bang. However, scientists are actively searching for indirect evidence of Hawking radiation using various techniques. One promising avenue is the study of analog gravity systems, laboratory-based systems that mimic the extreme conditions near a black hole's event horizon. These systems, such as Bose-Einstein condensates, allow researchers to create analogs of Hawking radiation and study its properties in a controlled environment. Another approach involves searching for the signatures of Hawking radiation in the cosmic microwave background radiation. The evaporation of primordial black holes, tiny black holes formed in the early universe, would have left a distinct imprint on the cosmic microwave background radiation, potentially detectable by future telescopes.